fitting problem briefly because it came up due to a question from one of you. And then we asked this question of whether the representation that we have studied is capable of representing surfaces of all kinds. And we found that there was a difficulty we encounter when the surface is not four-sided or bounded by four segments or four curves, right? So if I have a surface that has multiple boundaries, as in this case there are two, or if the boundary has more than four elements, right, then the representation that we had studied, like the NURBS or the Bezier or the parametric cubic, right, they will not suffice because these always map to a unit square, and therefore they will always be four-sided. Right, these will always be four-sided, surface patches. But real life, engineering artifacts, you will find that you will need, various cutouts in your surface, and therefore the question was, how do we represent that? And then we sort of highlighted that there are two parts to the representation now. One is what we call as geometry, which is the underlying surface that we start with, right, which is defined the way we have studied so far. And then we go in and identify the portions of that four-sided patch that we are interested in for this particular surface patch. We call it a trimmed patch, and we represent the boundary of that in the parametric space using the edges that form the boundary, right? So if I have the parametric space corresponding to a patch surface like this, right, a unit square, and then I mark my, the boundary in the parametric space, and I store that here, right? And together with these two, I am able to represent a trimmed patch. The way it works, we had also left this analogy with you, which is that the boundary of the trimmed surface patch, right, we can treat it like a cookie cutter, right? And so it defines the sort of contour that you want in your geometry, and you can choose to use the cookie cutter and cut the shape out of this surface which is given by this geometry. Now this geometry can be in a plane, it can be a curved surface which is convex or a concave, right? And accordingly the surface will change shape, the trimmed surface will change shape, but the connectivity or the boundary of the region of interest to you or us, right, will remain the same across these. So this is known as topology, and the surface on which you cut it is representing the geometry. Okay. So hitherto we were only focusing on geometry, but now we are looking at two parts in the information. One is geometry, which is your surface equation, the underlying surface equation, and the other is what books will call it topology, but essentially it defines the boundary as a list of edges. Okay, so what this means is that in my parametric space, if I take this to be a unit square, right, V and U, then I can have multiple boundary loops. So I have one boundary loop corresponding to the boundary and the two cutouts in the middle. My boundary itself can have multiple segments instead of four, right? It can be like this, right? So you can start with E1 here, then E2, E3, E4, E5, E6. That's the first loop. And the second loop could be, E7, E8, E9, E10. And then the next loop could be 11, E12, 13, 14, 15, 16, so forth, right? And so together these two will constitute the representation of the trimmed patch, right? And the main point that I would like to stress upon here is, apart from the fact that we are needing something other than geometry, is that this additional information, right, does not try and represent every point of interest to you. Okay, it only represents the boundary of the region of interest. Okay, because the region of interest to you is this entire hatched portion, right? And so in some sense, I'm interested in capturing all the points, but it turns out that all I need to do is to represent the boundary of this region, and that's good enough for me to, capture my representation. And it is not just the boundary, it is oriented boundary. These arrows here have a particular sense, right? They communicate the fact that if I traverse the boundary in this orientation, the region of interest to me lies always to my left, right? So there is a particular protocol associated with the representation of the boundary. So you should keep that in mind. Right? So trimmed surface patches, we take care of the underlying domain by geometry, and within that domain, the region of interest through these edges, which are in the parametric space, and that constitutes, the topology or the connectivity. Okay. Any questions so far? Okay. If there are no further questions, then I will start today's thing. Today we will let me just switch the phone off. Hang on a minute. Yes, somebody is trying to ask a question. Okay, if there are no questions, then I will continue. The next thing that we want to do is to look at the next higher dimension, which is solids. Okay. Now, before we go into this, let me just recap the sort of evolution of how this field took off. Remember, you may recall when we were looking at the evolution of the surface modeling side, we had touched upon the parallel developments in solid modeling. And like I said, the first sort of development happened, both actually in some sense came out of MIT early on, the numerical control of a machine tool, as well as this project called Sketchpad, which was Ivan Sutherland's PhD thesis, right? The numerical control programming system was primarily, to represent volumes that would be removed by machining. And in Sketchpad, the idea was that how can the user give inputs to the computer using a more convenient mechanism, and the Sketchpad was the outcome of that. And then, of course, there were software tools that started to be developed looking at representation of volumes for both manipulation by the computer and also rendering or drawing on the computer. And drawing on the computer was the first primary motivation, that how do you realistically draw 3D objects on the computer screen? And so one of the things that they first had to crack was how to represent the 3D object before they decide how to render it or draw it on the thing. So one of the first true 3D modeler, SDRC, which is now, actually, I don't even know who took who up. They had a software product called IISc. They merged with somebody and then somebody else took them over, but they are no longer existing, right, as a product, right? And then, of course, other systems started coming to play, right? And look at this thing. So I don't think that picture is there. Yeah, it's here. Okay, maybe we'll come back to this, and I'll not break the thing. Right? So the point is that this sort of developed in parallel with the development of surface modeling, and actually even till almost the end of 80s is when 70s, early 80s is when people started to think of how to keep the two together, namely solids and surfaces. Right. So till then, surfaces developed independently and solids developed independently. But since the 80s, we started seeing this combination in one modeling system, and that is the forerunner for the kind of solid modeling systems that you see today. So much like surfaces in solids also, the idea is that you want to have a unambiguous representation. Right. We will see some examples of ambiguity in the representations, but for now, what we mean is that it should communicate a unique object, and it should contain all pieces of information that you need about the object. Right. And an ambiguity essentially has to do with the point set that you are interested in, right? The material side that you are interested in. Right. So that must be clearly represented. And informationally complete, meaning that it has enough information to be able to answer questions of interest to you. Right. So right now I have listed 3 here, and they probably cover all the questions that you might want to ask. One is properties, right? Volume is a very simple example of the property. Right. Movement of inertia is another one that is tied to this property. Right. The second is, of course, point classification. And this is a question that we have been familiar with right from the beginning, right? That given a representation of the object, you must be able to answer this question of whether a point lies inside it or not. Right? So that's the completeness that you want, that you should be able to answer this question. And the last is, of course, what we call relational properties, meaning do 2 objects touch each other? Do they intersect each other? How far are they from each other? Right? If I cut one with the other, what do I get? So these are all relational properties. Okay. So the expectation in here now is that the representation must A, be consistent and unique, and B, must allow me to compute answers to questions such as these. Okay. So that's essentially what we want to do in solid modeling. And why are they required? As I said, it started with the visualization question, right? So you have a computer representing some 3D object, but unless the user sees it and gets a feedback on what is the object being designed, it is not very convenient or very useful for the user. And therefore, rendering or visualization was the first sort of motivation to look at solid models. Of course, cost of a product is always tied to the material that goes into the product. And the material that goes into the product is always tied to the volume, and therefore finding the volume of an object, complex objects typically, became of interest. And therefore, to find volume, you must have a representation of the 3D part, and therefore solid modeling became important. Then, of course, as you started using computer-based applications for other tasks, right, such as tool path generation, right? So there you want to know whether the tool, how much does it interfere with the part? Right? If you're doing robotics path planning, then you want to make sure that the tool on the robot does not interfere too much with the part. Likewise, if you want to do process planning, right, how to figure out how this part should be made, what is the sequence of steps to be used, then you want to know how much volume of material has to be removed to get an L step. right? And that again needs notion of a solid model. Lastly, of course, a new development called rapid prototyping or 3D printing or additive manufacturing, right? This technology again has become very attractive because it allows not just a 3D rendering on the computer, but actually a physical part that the designer and the management can hold in their hands and evaluate and critique. And that needs a solid model again, and therefore the motivation for having solid model representations have been going up steadily. Okay, so before we go into the types of solid models, I want to sort of show the continuity between what we have done in the past and what we're going to do right now, and the reason for any discontinuities. So we started with a curve, right? And we said that the curve can be seen as mapping from the parametric space, which is now a line segment, to my real space, right? That's my representation of a curve, which takes a parameter and maps and gives me a point in real space. Okay. Likewise, when we went to surfaces, my parametric space now became a square, right? With 2 degrees of freedom, u and v, and my surface representation, right, was enough to take any point uv in the parametric space and map it to a point xyz in the real space. And that mapping was given by your equation of the surface, representation of the surface. Now, there is an analogous extension to 3D, where now my degrees of freedom are 3, and therefore my parametric space becomes a cube, a unit cube, right? And the 3 degrees of freedom are denoted by u, v, and w. And like we did for curves and surfaces, it is conceivable, and we can think of this, that you take a point inside this tube, which is u, v, and w, and that maps into some 3D object that looks like that. Okay, and this can be some new representation, which is u, v, w. Okay, so that extension is possible. You can then, just like you did for the case of surfaces, you can think of writing, polynomial expressions which look like triple summations, right? I, j, k, n, m, and p, and let's say I have a, I, j, k, u power I, v power j, w power k. All this is possible. But we don't go this path. Can you tell me why?
So maybe the complexity increases.
Complexity increases, yes. Now you have not a tensor surface, but more complicated, surface of surface. Just like a surface was a curve of curves, now you have a solid which is the surface of surfaces, right? And so yes, it becomes complex to sort of imagine, but it is not complex to compute in some sense, because it is the computer that is doing the computation. The complexity comes in a slightly different way here, right? Which is that your definition of these AIJKs, right? If the definition of AI was painful in the case of the curve, and if it was cumbersome in the case of the surface AIJ, you can imagine that to do it in 3 directions or 3 dimensions will be even more hard. Likewise, control polygon grid now becomes, a 3-dimensional grid, right? And specifying that sitting in front of a flat computer screen, again, is a very painful exercise. If we could not define a grid of points for a surface, we definitely cannot be defining easily this grid of points for a solid. That's one complexity. but not so much in terms of the equations, etc. They are complex. I'm not, downplaying them. But since the computer is going to be processing it, it doesn't hurt us much. What hurts us more is the fact that you have to define these interactively for the computer to construct this representation. And that is a cumbersome and a painful exercise. And that is one bad thing. What is the second bad thing? The second bad thing, I hope, if you recollect, that's the last thing we did and we recapped it this morning, right? Which is that I have an inherent limitation in this kind of a mapping, right? That all my surfaces will be four-sided. Likewise, if I do this mapping, all my solids will be six-faced only. That is the nature of this mapping. I cannot go outside of this cube, and therefore my object will always be bounded by six faces, and therefore the only kind of solids I can create are either bricks or loaves of bread. Right? You can have different objects. You can have an object that goes like this, right? Or something that goes like this, or something that goes flat like that. But they will always have only six faces. And just like in the case of the surface, we said that your real surfaces will have cutouts, in them for facilitating entry of cables, exit of cables, and things like that, right? Or something to be attached here, that they'll never be four-sided. Likewise, you know already that the solids that you are interested in the real application will never be only six-faced. Right? You'll have pockets cut out, you'll have holes punched into that, and so you need a representation for all of that. And therefore, this analog extension from of using this parametric kind of representation does not carry over too well in 3 dimensions or for solids. Right? A, because it is not easy to define, and B, because we are always constrained to be having a six-faced object. And so it is that we will have a different type of representation scheme for solids as we go forward. So let's look at some examples. Right now, these are historically they evolved in this way. Right, wireframe happened first. Then came boundary representation, then came CSG. You will see what each of them mean. I'm just treat them as just simple names right now. We will see what they actually mean. Right. So, but there's another way to look at the representation of solid models, right? The one that the first one that is of interest to us immediately, we want to study this first, is that you see it as a collection of points. Okay, I have a whole bunch of points inside, and my representation is a representation of those points. But obviously, I'm not going to list every point X, Y, Z, right? We cannot do that. Right? So what we are looking for is what the mathematicians call a finite representation of an infinite set. So I have an infinite number of points in here, right? But my representation will be a finite one that we can get our heads around and write programs around, right? And the first of these is what is known as the decomposition model, and I will first start by looking at that. But before that, I think we have to go through the wireframe first. I think, yeah. So we will talk a bit about the wireframe. The wireframe representation, right, was one of the earliest representations for solid, and you can see the sort of motivation or the genesis of that in this picture here, right, where the operator, in this case, the researcher Ivan Sutherland, right, is trying to basically input a representation that can then be used by the computer to draw it on the screen. Okay, and the representation they came up with first was the wireframe. And as the name suggests, right, a wireframe is nothing but one that sketches the skeleton of the object, represents the skeleton of the object. So here we have an object which is a cube or a cuboid, right? And the skeleton basically consists of the 8 corners or the 8 vertices and the 12 edges that connect these corners. Right? That's essentially the wireframe representation. The nice thing about this was that, this representation was very easy to process given the computing power available those days. And as you can see, it is also easy to draw, right? Because all you need to do is to have a line connecting points. And that's all it was. But that was a tremendous, sort of a step forward those days. And therefore, this is indeed a landmark thesis project, right? By Avan Sutherland. Okay. Though the name CAD, story says is credited to Steve Coons and Dwight Bauman, who were faculty at MIT at that time. But the first work in representing solids that can be manipulated by the computer was done by Ivan Sutherland. Okay, so that's a wireframe representation. And why are we, not pursuing this further, right? Remember, we had said that we must have uniqueness and unambiguousness, right? So this is what happens with the wireframe. Right? So this is my wireframe representation, but you don't know whether it represents an object like this, or like this. So it is not unique, right? Some other information has to be made available so that the interpretation of that wireframe can be done correctly, that the object is having a hole going from front to back, top to bottom, or left to right. Right, so that's a non-uniqueness in the representation. The second question was about ambiguity, and that again is, an interesting one. And this is ambiguity not from the object itself. The object is the same, but from the view of the object or the orientation or the configuration of the object. So the same wireframe, right, can have these two possibilities, right, of the object, right, and they will result in the same wireframe. And therefore, it causes ambiguity in terms of understanding the configuration or orientation of the object. And therefore, the wireframe is not a good or a convenient representation to pursue, though in terms of quick feedback, right, it is very attractive. Right? So the moment you design the object, a wireframe can be quickly drawn, and people can see it. Of course, like I said, these ambiguities remain, but if it gives feedback that everything is there, fine, we can go proceed with other modeling changes, it becomes a very convenient exercise, right? And therefore, this is attractive still. Now I want to start talking about this decomposition-based model. And essentially, the idea, as I said, is that you want to represent a set of points, right? That's the goal. The volume is a set of points, right? And the point set based methods, of which decomposition based model is one of them, right? You want to represent the set of points, but as I said, you don't represent all the points, right? That's not physically feasible, right? And therefore, we do two things, right? One is we sort of do an enumeration of the space occupied by the object. Now, you may remember, finding the area of an arbitrary shaped object in your school days, right? How would you do that? You would embed that shape on a graph paper and go and mark off the cells in the graph paper that are occupied by the object. And that's your representation. The cells that are occupied by the object are your representation. Right? So in some sense, this is, we are enumerating all the points, but not representing all the points. We are only representing the cells which contain some of the points belonging to the object. Right? Every other cell contains no point in the object, so we don't worry about it. We only worry about the cells that are shaded gray here. That represents my object. So the reason why you did this in your school was because then you can find the area by adding these cells. You know the area of one square, and by adding and multiplying by the area of one square, you can find out the area of this. That's very attractive, right? Very fast. The second question that needs to be asked, remember we had said was one of point classification. Now, supposing you want to find whether a point is inside this object or not, you just need to know which cell this point lies in. And if that cell is outside, the point is outside. If the cell is inside, the point is inside. So that too becomes very easy, right? Because given a regular grid, right, a grid like this, it is very easy for you to sort of quickly find out which, given a point, very quickly find out which cell the point lies in. And then you have a label on every cell, and therefore you can quickly decide whether the point is inside or outside. Right. So this is one example of a decomposition based model where I sort of cluster these points into these cells and use the cells to represent the object. That's the decomposition I do, right? There's a slightly different way that you can do the decomposition. Right? Instead of having a uniform sort of a grid of cells, right, and then enumerating which cells have points containing belonging to the object, you do it the other way around. You divide it from the top down, right? You start with a large cell, and then you divide them into smaller and smaller cells, depending on whether you need further subdivision or not. So here, if you see, right, this is actually a 3D example. So strictly speaking, this should be of tree, right? But as you can see here, right, I start with a large cube which contains my object that is shaded. Then I divide the object into 8 sub-octets, cells, right? 1, 2, 3, 4, and bottom 1, 2, 3, 4. Right? If I divide each edge in half, I will get this number of cubes, and then I classify these cubes again. There are some cubes that are completely filled, which are in black, some cubes that are completely empty, which are in white, and some that are partial, which is half black, half white. So here is the advantage now of this scheme, is that you don't now touch any of these that are either full or empty. You only divide those that are partial. So this gets divided into 8 octants again. So this corner piece here gets divided into another 8. And then again, you classify it and you find that the one is full and the remaining are completely empty. And therefore, this becomes my representation. The reason for this is that, that you're using much less number of cells, right? Because instead of storing, I don't know how many cells in the previous picture, here you need to store only 1, 2, and 3. Except that this is of a different size based on the level it is in. And this is a different size based on the level it is in, right? So this will be exactly half of this or 1/4 of this, right? And so you should divide that accordingly. So I start with 1, here the size is half, here the size will be 1/4, right? So conciseness becomes a very attractive feature, right? You are storing much less number of cells here as compared to the previous one. But the price you pay is that you cannot just count the number of cells and find the properties. You have to count the number of cells at each level and then find the property at each level and then add them up. So for example, here, if you're finding volume, if you say I have 2 here, then the volume associated with them is different. And I have 1 here, the volume associated with that is different. So that has to be kept track of. So the level number has to be constantly associated with these cells. right? So that's one type of a representation. One where it is the equivalent of a graph paper in 3D, right? I have a lot of cells, each uniform size, and then I embed my object in it and mark off the cells which are occupied by the object. The other way is that I start with a larger box and then subdivide, right? Based on occupancy or non-occupancy or partial occupancy, and keep dividing it till I can break it completely into filled and unfilled cells. So those are the two, spatial enumeration stroke decomposition based ideas, right? But and I have listed the advantages here in both cases, right? The advantages are that computing properties is an arithmetic operation. What I mean by that is that there is no major computation to be done. You just have to count the number of cells at each level multiplied by the volume associated at that level. So if I start with a unit volume here, this will be, 1/8 of the volume, and this will be, again, 1/2 of that volume, 1/8 again, so 1/64 of that volume, and I keep adding it up. Okay. So that's the difference. But in the case of the cell, I just have to count the number of cells. I know the volume of each cell, and that gives me the volume directly. So properties are just simple arithmetic. There is no computation. Second is classification. Right? Now that is also convenient, right? Because, you given a point, you can find out which octant it is in. And then if that octant is labeled full or empty, you know the conclusion. If it is partial, anyway, you will have these octants, so you know which octant that is, and you can always decide whether it is full or empty. So those are the good things about this representation. Can you tell me what are the negative things about this representation? What is bad about this representation?
So like we have the square or maybe the cuboidal graph here. So if we have a cylindrical hole in the
yes.
bar, so yes, we can't determine the area which is cut out.
Exactly. Because you can see the example here, right? The actual area of the object you get is actually off by the area enclosed by these caudal segments or by these, things which are inside the hole. This is meant to be a hole, but my shape of the hole is now, somewhat strange. It's not circular, right? And for me to get a better approximation, I have to reduce the size of the cells, right? Then I can do a better job of trying to get as close to the circle as possible. So the first negative thing is that this is approximate. It can never be exact. And it need not be even curved. As you can see here, this inclined edge here, right, will again cause you problems because this much volume is not there in the part. This area is not in the part. But because I take the whole cell as occupied, I have to, count that, and therefore I make a mistake in my computation of the area. Okay, and therefore that's a bad thing. Any other negative thing that you can think of other than approximation? Okay, what do I mean by this? How do you create a representation of either the cell-based enumeration or the octree or the quad tree from scratch? So you have some shape that you want to create, right? Clearly, it is very difficult for you to take a graph paper, right, and start filling out, and design your part like this. You're not going to design your part like this, right? It will take you ages to design a 3D part by creating the cells that are going to be filled by the object. So what this is saying is that I cannot create this representation from scratch. I need some other representation to compute this representation, right? For the user to create the representation that these cells are marked and the remaining cells are not marked, right, is impossible for complex objects. For simple T, yes, it is easy. I can always say these 3, 4 are occupied, everything else is unoccupied. But for a complex object, like for example, this one here, right, there's no way that you can go and draw these cells are filled and these are not filled, and therefore that's my object. You have to have some object representation that you already have, which you can embed into this grid and then mark off the cells that are filled. So that's the second bad thing about this representation, which is that you cannot construct it from scratch. You have to have another representation to be able to build this representation. Right? So those are the two limitations, and the two positive things, of course, are that it is very fast in terms of computation, both for computing properties and for classifying points with respect to the object. Okay. And some of you may also see that, if you take an application like finite element methods, right, numerical computational schemes, they all are looking for elements like these. And therefore, this representation is very amenable to pass it to a finite element tool. That's another advantage, but these are the two main advantages, and these are the two main disadvantages. And therefore, the whole idea of this point set being enumerated using cells or octrees, right, is not very attractive, because you need a different representation first to start with. And so now we are back to square one as to what that representation should be. Right? So I go back again to this picture here. This picture here. Right? So I cannot use this because, as I said, it is confining me to 6-phase. I cannot use the spatial enumeration because, of the limitations that I cannot do this on my own from scratch. It has to be done after I have some representation. So what's the solution? What is the representation that is possible then? Well, it turns out that we have already seen the solution, which is the case of the trimmed patches. Right? The trimmed patches basically address the problem that we had, similar problems, right? That my regular representation can only do 4-sided patches. But if I need multiple-sided patches, then I must have another piece of information, which is geometry and topology. And the topology basically is given by boundary, right? But oriented. Right? So an oriented boundary gives me the representation I need for arbitrary objects or surface patches. So if the big problem here is that my objects are always going to be 6-phased if I go with this representation, then it seems that maybe this is what we should do, right? That instead of trying to represent it like this, we represent it by its bounding entities. For a surface, the boundary is a curve, right? For a solid, it will be a surface, right? And therefore, that's what we do next, which is that we try and represent the object by its boundary. Right? And so if I have a sphere, just to give you a feel that it is a 3D entity, right? A sphere. Then I can represent it by its bounding surface, which is nothing but x square plus y square plus z square minus 1. So that's a unit radius sphere centered at the origin. But that's not enough. That's alone is not enough. We said it must be oriented boundary. So how do we fix that? We fix that by adding an orientation with a convention. And what is the fixes the orientation of a surface? It's normal, right? So we say that the normal of the surface always points away from material. Just like in 2D, we say that it is that always to the left of the traversal direction. Here, it is always in the direction below or away from the direction of the normal. So then if I'm standing there with my head along the arrow, then material is at my feet. That's what this means. Right? So that becomes a representation of a solid. So an n and this expression, that becomes my representation. So mind you, this is not a representation of a solid, the equation. It represents a surface. And that orientation is the orientation of the surface. So with the bounding surface and its orientation, I am able to represent the solid. Right? Because with this expression, I can tell you whether a point is inside or outside. I can draw this, I can cut and tell you, what it looks like inside. I can intersect it with any object. All those things are possible. So this is a representation. But what is the problem with this representation? The problem with this representation is the same one that we saw earlier, right? Which is that how many solids do we have which has a single nice continuous bounding surface? If I look at my brick, right, I don't have a single bounding surface. My bounding surface, in fact, is discontinuous here. Right? Because I have one surface here, another surface here, and there's a discontinuity here. Likewise, one surface here, another surface on the back, and this is a discontinuity. Likewise, one surface here, one surface in the front, that's a discontinuity. Right? So what this is saying is that my bounding surface is no longer one surface or one patch, but rather a set of patches. And we have a qualifier here, we call them quasi-disjoint patches. What do I mean by that? By quasi-disjoint, I mean that the patches touch each other only at their boundaries. So that's what is happening here. I have patch 1, patch 2, they touch at this boundary. I have patch 1 and patch 5, they touch each other at their boundary. Likewise, right? So I have 6 patches, each of them quasi-disjoint with the others. So my representation of a solid is no longer one bounding surface, but a set of what we now call faces. Right? The bounding surface is discontinuous, and the discontinuities divide the bounding surface into quasi-disjoint patches called faces. So each of them is a face here. 1, 2, 3, 4, 5, 6. Right? Now, how do I define a face? How do I represent a face? We have already done this, right? We represent it by its boundary. And what is the boundary of a face? It's a curve. Again, I can have one smooth curve, or I can have a bunch of quasi-disjoint curves. And therefore, my set of faces in turn is represented by a set of what we call edges. And edges are nothing but quasi-disjoint curve segments which bound a face. Again, quasi-disjoint, why? Because they touch each other only at their boundary. Boundary of a curve is a point, and therefore the neighboring curves touch each other only at points, and therefore they are quasi-disjoint. And lastly, each edge in turn is bound by two vertices, V1, V2. So I have V1, V2, V2, V3, V3, V4, V4. So that completes my representation of a solid. Okay, that constitutes, sorry, 1 second. What time is it? Oh, almost. Okay, no problem. So that constitutes a representation of my solid. We started with the notion that I can have an oriented bounding surface, which will be enough to represent the solid. But then we find that my objects will not have a single bounding surface, and therefore I get into this notion of faces, which are quasi-disjoint patches that form the bounding surface. I have edges, which are quasi-disjoint curve segments that form the bounding faces, patches, and then each edge in turn is bound by the two vertices. Okay, so that representation is known as boundary representation, or written as BREP, BREP as two words, BREP as a single word. Right? So all these notations are okay. Books will follow different ones. Okay, fine. So now, you know, we have some feel for how a solid will be represented. We can now start looking at the details of what that representation entails. I'll stop here, and if you have any quick questions, I'll answer them now. Otherwise, we'll pick it up on Wednesday. Any questions? Okay. Then I'll stop here, and we can continue from this point on Wednesday. Right? Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Thank you.